Hey class, I hope everyone is doing well. We are back here talking about ecology, and today we begin our next discipline, that is population ecology. I hope you did well on your first lecture test. Your second lecture test will be population ecology and community ecology, and today, or this week, is part one of population ecology. We're going to talk about the basics of population ecology, what a population ecologist does, the challenges of population ecology and being a population ecologist, as well as the concepts of abundance and how to determine abundance. And you'll be doing this in lab, hopefully, as far as practicing these techniques in the field, not just for one lab, but throughout the course. We will be retouching on all of these. Oh, the parrot's back. I'm gonna move. Sorry. Okay. Sorry, Ruby. All right, let me move. So, as you may recall from our introductory lecture, that we study species in species ecology, and when we now take into consideration one given species in a geographic location, a grouping of said species, now we're talking about a population. And let me move even further away. Okay, sorry about that. Anyway, and that geographic location can be whatever you decide that to be. It can be the population, as I used before, population of turtles in Green Pond, or population of eastern painted turtles in Green Pond, or a population of eastern painted turtles in Pennsylvania. As long as you're only discussing one species in that geographic area. The key here, as far as what population ecologists do, is their main role in this discipline is, there are many, but their main role is finding out the overall abundance of any given individual, or I'm sorry, any given individuals in any given geographic area of that particular species. How many of them are there? Abundance is just a fancy word, or not so fancy word, to indicate that. The density is how many are in any given like square mile or foot or even inch, if you're talking about bacteria, in that given area, or I should say blades of grass. It's a little bit more applicable to what we're going to be doing out in the field. And easy enough, right? Well, not so much, we are doing things out in the field, out in nature. So sometimes determining the abundance can be somewhat of a challenge. Now, of what you can do, it depends on what your hypothesis is, or what your research question is. As I'm jumping down here to what we would refer to as presence and absence data. Presence and absence data, as far as whether the individuals of your species are there or not. That could be sighting the plant or the animal. It could also be signs. Sometimes you never see or rarely see an animal, but you could hear them. A lot of tree frogs are like this, as well as some species of very elusive birds. Sometimes you see the tracks of an animal, like deer tracks through the woods. You might not see the deer, but you know that they are there because you can see the tracks that they leave behind. A scat is a very fancy way to say poop. And sure, animals poop in the woods, right? And if you find their poop, and believe it or not, there is a science to this, and there are even field guides dedicated to what type of scat belongs to what type of animal, because poop looks different. Example close to home for me is that I live along the Palmer Bikeway, and in my little townhome neighborhood, for the past 10 years, you've heard people say, "Oh yeah, I saw a bear in the woods, I saw a bear in the backyard," and I'm in Easton, and it's kind of like, well, okay, probably, but I don't know, maybe it was a big dog or a small or big cat or something. But just in the past month, I saw bear scat on the trail. So yes, there was absolutely a bear there because I saw where it pooped. So I can say definitively, even though I've never seen one, that there is definitely a bear, at least one, in the woods because I saw its scat. Now, that leads me to an important note here, and that is that you can use what we refer to here as indices of abundance, this presence absence data. You can use this in saying, you go so far as saying there are a lot of deer in the woods. I see a lot of deer prints. I hear a lot of tree frogs. So we know that there are, like, let's just say gray tree frogs that are common in this area. I hear a lot of gray tree frogs. You can also say, I saw one example of bear scat in the woods. So there might be one there, or I only hear one gray tree frog. So I hear very few. So there might be a few in the woods, but you can't generate an actual number from what we call these indices of abundance. You can't scientifically say, I see a lot of deer tracks in the woods, so therefore we approximate there are 25. Or I hear a lot of gray tree frogs in the woods, so scientifically I can estimate that there are 40. You do not generate an actual number. You cannot. It's not scientifically valid using such data or using the indices of abundance strategy. That is only a presence absence. You can say that you believe there are a lot of them or very few, but you don't generate an actual numerical set of data. Now, going up here, of course, as a population ecologist, it's best to know the exact number. This is a very rare that a species ecologist knows the exact number, unless it's a limited study, like I have the example here. And I honestly don't know how many white pine trees are on campus. It's just an example. But if you wanted to know how many white pine trees were on campus, it might take a while. We have a pretty big campus. But if we can directly count them, then good on us. That's what you want, an absolute number through what we call a direct count. If that is possible, awesome. There are 25 white pine trees on campus because we went out and we counted all of them. Okay, that's great. Or you have a meter square. So the population in a meter square of seafloor of a certain type of sea star are 4. That's the population within that meter square. Perfect. Now, however, often this cannot be done. And what we do is we have to resort to, which is scientifically valid in the absence of being able to directly count. And mostly what we do as population ecologists when determining abundance is we form population estimates. We estimate a population. We can give a range. And when you hear about the population of elephants in the wild, we hope that there are more than we can directly count. That would be bad for a species if the only, we can directly count the number of them left in the wild. So we would estimate, I'm just, again, pulling this out of the sky, but say there are 5,000 elephants left in this particular country in the continent of Africa. It's an estimate because most of the time it's impossible to count directly, or there might be too many of said individuals in a population, or they might be elusive. Like, how many eastern painted turtles are in Green Pond? Well, in the absence of draining the entire pond, we can't, it's impossible. Green Pond is too murky. We don't have the equipment. We would not be able to tell. So we go about these certain methods to form these population estimates. Now, if you have those individuals that are sessile, that is, they don't move, We can employ quadrat methods. Sometimes they are like square quadrats, and we're going to do this for lab, if we meet for lab. Or we have line transects as far as point sampling is concerned to form an estimate. And you see an example here. This is a quadrat. I don't know what this person is counting on the seafloor. Here is a plot split into quadrats. We'll go over this first and then get back to the seafloor one, see if this is gonna, there we go, that's better. So with the quadrat method, you basically have a plot, an area of study, okay, how many milkweed, or no, let's use a different example and you'll see why if we do this lab. How many dandelions are in this 10 meter by 10 meter plot of meadow? And to count all of them, it would be very difficult to do. So what we do is we measure out 10 meters by 10 meters, and then we delineate that into these 101 meter quadrats. And then what we do is we randomly select. You can have fancy computer equipment to randomly select these 1 meter squares. We go as far as technology is concerned by blindly throwing a ping pong ball or a tennis ball in the middle of our plot. Works just as well. And then you only you would only count the number of dandelions within one of these little 1 meter areas. And you might, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It looks like they picked 11 of these little plots. So say we have 11 students, so we would have 11 students count up directly how many dandelions are in a 1 meter section. Yeah, you know what? What's the example? Why don't we do the example instead of 11? Sorry about that. Like they pick 11, we're going to say 5. So delineate the plot into quadrats. You randomly choose how many plots. Let's say we're going to choose 5 different quadrats to count them up. You count 80 individuals in 5 quadrats. You add up the individuals and divide by the number of quadrats. Why did I have that 4 there? You know what? Anyway, I'm sorry. I don't want to start all over again. You add up the number of individuals in all of the quadrats. Thank you very much. You divide by how many quadrats you chose to give you the average number. I'm going to have to change this in the static version. The average number in each quadrat by dividing how many quadrats you have. And that gives you the average number in each quadrat. And then what you do is you multiply, and what we have here, again, these numbers aren't agreeing with one another, but if you average out that there are 20 dandelions per quadrat, you multiply that by 100 total quadrats in the entire plot, and it gives you 2,000 individuals, an estimate of 2,000 individuals in that particular plot. And we can do some statistics. They're called like degrees of freedom and confidence intervals, where we can then calculate that with 95% confidence that there are between just say 1,800 and 2,200 dandelions in this entire plot. I'm not going to go through that here. But when one would do such a study, a quadrat study, just like any estimate, you would say that that was the method that you used. You would use the term estimate. We estimate that there are 2,000 dandelions in this plot using a quadrat method. You would not say there are exactly 2,000 because you don't know if there are. It's just an estimate. But scientifically valid in the absence of being able to individually count. This works best, this quadrat method, if you have this regular distribution that you see here, this pattern. If you have different types of distribution, like for instance, if you have a clumped distribution and you randomly choose your quadrats within the plot, Sometimes it can give you a bit of a lower number if for some reason you wind up choosing plots or selecting plots that have none in them, no dandelions, and obviously they're there, but they're clumped in, kind of clumped together. So it could give you a bit of a low number, or if a quadrat is chosen where there's a bunch clumped together, it could give you an artificially high number. Um, Therefore, it's best you generate your most accurate estimates when you choose more quadrats within any given plot. These line transects or belt sampling, line sampling, point sampling. This is the same except you're not working with a square. Instead, you're working with a straight line with these quadrats that are set up along a straight line and not a squared plot. So that's for things that don't move much. I mean, plants, obviously. But you do have animals that don't really move a whole bunch. Well, you have animals that really don't move at all in many of their life stages. Like if you're estimating how many clams or oysters are in any given area, or mussels in any given area, because they're fixed to a substrate, but mostly for plants. Or you can even do this with animals that move, but really, really slow, like sea stars. They don't really move much or very far, so you can do this quadrat method with them as well. Sorry again about, the numbers are a little messed up. I'll have to change that. But let's just say you're a population ecologist and you want to estimate for a species that is moving around and doesn't want to be seen. What we do here is we employ a method referred to as, or one of these methods is referred to mark and recapture. Now you can actually capture, mark, and recapture. It's often just called mark and recapture, but you're capturing, marking, then recapturing. Kind of to put it out there is that this can be done through sighting and not physical trapping, but just as an overview as far as how this is used, and then go on to some of the complexities with trapping and then marking animals. It sounds a whole lot easier said than done. Of course, it's nice and tiny here on a slide, but we'll get into the challenges of that. You use the method of capture, mark, and recapture, and then the math that you use is a Lincoln-Peterson estimate. You can also use a Schnabel estimate, and we'll differentiate that in lab. Lincoln-Peterson is for kind of a once and done. A Schnabel estimate is used for over long periods of time where you're constantly capturing, recapturing, capturing, recapturing. And basically what it is again, this is like the simplified explanation overview, is you capture the animal or animals, you mark them somehow, so you know you've captured them. You release them back into the wild, and then after a given period of time, it could be a day, it could be a week, you put your traps back in, and then you capture more animals, and you inevitably will recapture some that you've captured before. You know that because you marked them, and then you capture ones that you haven't marked, some new ones. And the estimate of the population, just through some kind of simple math, is basically just a ratio of how many new ones you've recaptured the second time versus ones you had recaptured. See that right? Yeah, new ones that you captured during the second trapping versus ones that you recaptured during the second trapping. So, like for instance, we can look here. You capture and mark 39 turtles on trap day 1. That's your big M. And then a week later, you put your traps in. That's your second trapping. And you capture 34 turtles, which is your little N. 15 of those were previously marked, and then 19 are new. And so it is just little n times m divided by r. So little n is how many you capture the second time. Big M is how many you capture your first time, divided by how many you recapture. That's 15. And your population estimate is 88. So you can, again, use some confidence intervals to give you a range instead of like one number. Like you estimate that there are 88 turtles, eastern painted turtles in Green Pond based on your mark recapture study, but we're 95% confident that that number is between, for instance, 80 and like 94, no, 96 for your confidence interval. So, and this is a picture showing turtles being trapped here in a trap, I should say, and this is marking a turtle. You know, hey, it's like I keep saying, this is a tidy, very sterile explanation of the process. But as a field ecologist, to do a population study, oh, it can be very challenging. It can be messy. It can be dangerous. It can be expensive. It can be a lot of hard work. I should say always rewarding if it's what you want to do, but you know, depending upon the animal, and you would talk to your species ecologist as far as some of its behavioral or physical traits, as far as how to best capture these animals to undertake such a study. Depending on what what method you would use, what traps you would use, and I put some of these here. For instance, let me see where do we start? This is called a mist net. Now, in one of your learning activities, you do see them employ mist nets for songbirds. It's a very finely meshed, like a filament net. There is no bait involved with this. You're not luring them in with food. You can lure them in with calls if you have birds or bats. This is also used for bats that respond to a call. Then you can use that, or otherwise they're just put in an area that is a common flyway, because the bats and the birds don't see these. They can't sense them, so they fly into these and they can get trapped in these nets. So I know with the saw-whet owl study, they use calls to lure the saw-whet owls to their traps. Now, these traps are attended to. They're not left alone, and the animal is generally removed from this trap within a few minutes after it being trapped. So this is a very active type of trap. Now, back up a bit. With all of these traps, of course, you're not, the intention is not to kill the animal and to do as little harm as possible, which physical harm, psychological harm, obviously there's going to be a little bit of stress involved, but you do want to be sure that the animals are not injured in any way. And that being said, you aren't injured in any way either. So this is a mist net. It's commonly used. John Leiser, my counterpart at the Monroe campus, uses mist netting and to trap songbirds for his ecology students. I don't know if he's doing it this year because of COVID. This is another trap that's used for birds, but specifically birds of prey. It's called a Balfour snap trap. And this is laid open and bait is put here in the middle. The bird of prey sees that and flies down to capture it, and upon landing on it, it trips the trap to close over that bird of prey, like hawks, for instance. Well, butterfly nets, we've been using those for a very long time. If you're trapping insects, you would use a sweeping net technique. In a meadow, for instance, you'd sweep your net back and forth to capture insects. Butterflies, you kind of have to chase down a little bit more actively. That's a common method that is used to trap bugs. You can capture frogs with these as well. Different types of aquatic nets to capture frogs. You have here, this is trap and what it, whoops, get rid of that. Close. Thank you. This is a pitfall trap, And what you have, or what you're exploiting as far as behavior with animals, is that when you have animals that crawl along the ground, certain species of reptiles and amphibians, if they hit like a wall here and you see these nets, generally what they'll do if they can't crawl over it is they'll just walk along it until they can go around it. And so you position these little nets, these little walls, to the center here. This basically it's just a buried bucket, and it oftentimes they'll have a like a little umbrella over it. And what happens is the animal just walks along that fence until it falls into the bucket and can't get out. Sometimes you grease the top of the bucket so they can't get out. And then the ecologist will go ahead and they'll collect the bucket. You make sure you don't want to use these in the rain because you don't want your animal to drown. This is a baited hoop trap. There's turtles right there. And this is what we use out at Green Pond. So you'll hopefully be seeing a lot of that. And it baited, meaning that this is one of the traps that you would lure another trap, I should say, you'd lure the animal in with food. Turtles have a great sense of, water turtles under the water have a great sense of smell. So we use sardines in our trap because even though there aren't sardines natural to, for instance, Green Pond, same way there aren't Cinnabon trees out in the wild, they are super yummy and attracts turtles. And so we find those to be most optimal. Oh, how do I pause this? Okay. And so that lures the animal into the trap that way. You also have baited traps. For instance, this is a bear trap, and it's kind of like a spring load, like a guillotine door. It doesn't chop its head off, but this is open, and it's baited with, again, not something you'd find in the wild, but something extra tasty. Donuts is the favorite food used to lure a bear into a trap. The bear goes in and trips kind of a little spring-loaded thing, and then the door comes down, and then the bear is trapped. This is one that I was hoping we could use in the field, but unfortunately, they almost always get stolen. We've had several of these throughout the years, and people borrow them and don't bring them back to us. This is called a Sherman trap, and the Sherman trap is for small mammals. And you put food in the back of the trap, and the animal goes in. You put it along like a walkway where you know that the animal will be, or like you see like in fields, you see actually little paths in tall grass where mammals frequent. It's almost like a little highway system. You put it along there, the animal goes in, it trips like a little trap door and then closes. We even get a little bit more savvy, or use a little bit more, technology here, get a little more complicated. What you're doing here is you are catching fish through electroshock fishing, which you see these two people here with the backpacks, the electroshocks and probes, and the person behind them has a net. And what you do to catch fish en masse is you stick electrical probes in the water, just real slight, with a slight charge, and you kind of zap that section of water, and the fish are stunned, and the person behind captures them with a net, puts them in a bucket. You process them as far as studying them, and then you release them back into the water. You can even go as far as chemical restraint. Now, this is like big time types of trapping method. As you see, this tiger has a dart here that has anesthesia in it. And when you're dealing with very large, dangerous animals, this is what you often have to resort to. That is anesthetizing them some way. And this requires lots of hands-on experience, obviously, an on-site veterinarian to revive the animal. But it is definitely a method that is used in situations where you are trapping an animal for means of individual or for study and for population study. So, all right, we've trapped the animal. So then how do we mark the animal? Oh my goodness, because you want to know in an abundance study, an estimate, a population estimate, you do want to know how many of them are there, and you want to know if you captured, you should say that the animal that you marked was captured before. Now, there are some markings that will just indicate that you've captured the animal before, and then like that's it. But then there are also markings which indicates that not only did you capture the animal, but that you have traced that individual back to, or you have a marking that's unique to that individual of that population with a series of like numbers or letters, for instance. Now, whenever you're doing a marking type of exercise, you absolutely want to make sure that you are safe. You want to make sure that the animal is harmed as little as possible. And there are certain methods of restraint that are unique to each particular species to avoid both of those scenarios, which have improved over time, as you'll see. Some are no longer done in the field because they've fallen out of favor from an ethical standpoint. You also just want to say that you may just be doing a mark recapture study, but while you've gone to all the effort of purchasing equipment, putting equipment out, getting the field power as far as people who are monitoring this equipment and who are taking care or going to the effort of trapping and marking these animals. Oh, you know what? That's the FedEx guy. And I don't want to start this whole PowerPoint over, so just give me a second. So, oh, thank you so much. Cheers. Have a good day. Is that while the animal is in hand, that you don't just want to mark the animal and release it. Sorry, the dog barking at the FedEx guy. But you also want to get as much data and information on that animal as you possibly can for future studies, whatever time allows. Like, for instance, for our mark recapture study on turtles, if we just want to do a Lincoln Peterson, estimate, we would mark them, we could just mark them and release them. But while we have that animal in hand, while we've gone to all that trouble, we're going to measure the animal. We're going to check it for any health problems. We're going to check if it's gravid, if it has eggs. We're going to weigh the animal. And then release it. It may take an extra minute or two to collect all of that data. It may have nothing to do with what your study is at the time, but collecting that data while you have the animal in hand, it can be invaluable for the conservation of that animal or to study that animal in the future. So that is something that is often done. So some marking is a bit more covert than others, and I know you have learning activity that does go through some of these. You do see links down here, but the one with sharks you're going to do in a learning activity later in the course, and also with birds, and you have one with snakes too. But anyway, this is marking a squirrel. Now, we used to mark squirrels with very colorful ear tags and very large, just because that way, if you're doing a follow-up study, you have a nice red ear tag on a squirrel, and as a researcher, you could walk through the woods and, you don't even need binoculars. You can just look and you could see what squirrels you tagged before. It was great. Unfortunately, birds of prey who love to eat squirrels have great, can see in color, right? And so what we were noticing as researchers that not only could we see them for the sake of our study, but the birds of prey could see them to eat them. So we switched to kind of inconspicuous types of ear tags. You see it's a metal one and you can barely see it, and neither can the bird of prey. So that's something, unfortunately, we learned as researchers the hard way. Those animals that aren't prone to predation in their given area, you can use this. This is a sticker that's used on the back of a water turtle, red belly turtle 61. So when it's basking, we can take a look through our binoculars and we can recite it. Now for our turtles in Green Pond, and if we've been to Green Pond already, you've already seen this, is you have these numbers that are assigned to the outer scutes, the outer shell, the outer margins of the shell, and then you can individually mark this animal by filing different notches in depending on the scute. Now these are numbered, usually they are lettered. This does not hurt the turtle and it stays the lifetime of the turtle. It's like filing a fingernail. But if we designate certain scutes as like A, B, and C, and we want the turtle to be turtle B, we can put a file in that particular turtle, just scute B, and we know, we'll say like turtle B is a female and it's 100 millimeters long and it weighs 90 grams. And then if we capture it the following year, we can remeasure it. Well, now it's 110 millimeters and now it weighs 120 grams. And we can measure growth rate that way. Unfortunately, this is the marking that was done, that used to be done. It's still done very rarely, unfortunately, a way of measuring, or I should say marking amphibians for life. And that is that in the same way you have letters or numbers designated to the outer margins of the scutes on turtles, is that the digits and the digits are given numbers on frogs, for instance. And if you wanted to mark a frog, what you would do is use a toenail clippers and you'd clip off parts of its toe. Like if this toe were toe B, you would clip that part of the, here we go, you'd clip that part of the toe off, and then you would forever know that frog as toe B. Now that's clipping off toes, ugh, that hurts the animal, but turtles filing does not. And so we've come up with a different method, and that's what you see here. And that is you inject under the skin colored like a dye, almost like a resin. It's right between the toes, and it's this bright kind of green and very small, so it can't be really detected by predators. And each is injected under the skin in different parts of the feet, not as painful as the toe clipping, but that is a way of marking amphibians. It's also a way of marking fish. It's really hard to see here. It's very tiny. There we go. But you can also inject a small amount of dye right by the eye on a fish. You can also do an adipose fin clip. You do see that as far as the fish, marking a fish is concerned. We've also gotten a little savvy too. Like we see something doesn't work, we can change how we do things. Leg bands on birds. Flighted birds are a very common way of marking them, bird banding. In geese, not a good idea. And what we found when we were doing leg bands, although some places still do, is that sometimes what they swim in, like if it has a lot of algae in the pond or water plants, it can get tangled up in a leg band, and the bird isn't able to fly that well. And so they switch to neck bands in most areas because that does not interfere with the natural habits of that particular animal. If we are able to do this, I sure hope we are, this is a sticker that is individual to this monarch. It's done through University of Kansas, although other institutions do these types of studies with monarchs. Monarch populations are crashing, unfortunately, as you may or may not know. These stickers all have individual numbers on them. And what you do before you release them is you put this sticker on with that number, you record whether it's a male or female and where it was released. And then there are those who, if they find a butterfly, a dead one or a live one, they can actually report the number. And so researchers can track, their migration habits. So that's actually a really great marking technique. You also have let's go up here, these electronic means, and you'll see that with the snake video for your learning activity. And that is, this is a fish that they're marking, and this is called a fish board. And they've restrained the fish, and they put a little, like, kind of like put in a little pit tag, they're called. It's the same thing if you have a dog or a cat that has a home again chip, where they scan it and it then gives them the information electronically. This is put into, a pit tag is being put into a fish. So you can mark in that way. There's a limitation to pit tagging, and that is that you can't physically tell that the animal has been marked. You need to have a scanner in order to do that. So, but if you have a scanner, that works out for you. The other means here, as far as kind of it's not mark recapture, but if your animal can't be tagged, you can digitally photo document it and do like a cite and recite type of study and generate estimates that way. And like, for instance, the back fins and the dorsal fins of certain whales are very uniquely shaped as well as colored to the individual. And so you can photo document these and feed them into a software program who can then individualize that particular animal and indicate whether or not it's been recited or not. Okay, well, there are your complexities of determining abundance. Direct counts are awesome, but often can't be done. Your presence, absence, or indices of abundance will not generate numbers, but will at least let you know whether or not the animal is present or absent. And the complexity, or I should say, I'm sorry, the population estimates if your animal doesn't move versus or plant using quadrat methods or line transects. And then you have these methods that are employed if you have animals that move around a lot, different methods of capturing and different methods of marking. Just some of the fun you can have if you decide to become a population ecologist. All right. Hope that you enjoyed the lecture. Hope you enjoyed our chat. If you have any questions, you can go ahead and put them in the discussion portion. Okay, take care. Sorry for all the interruptions with the FedEx guy and the parrot and the dogs. But hey, that's what you get with live theater. Take care. Bye-bye.